for the invitation, for all the wonderful organization, and for all of you that dedicated to participate. So indeed, what I'll be talking about is something known as homomorphic secret sharing, but I'll be telling you what this is. So let me begin actually, in any lattice-based workshop, typically there'll be at least one or a couple talks talking about fully homomorphic encryption. This is not what I'm talking about in this talk. But I do want to mention it to start with because this is a useful analog for what we're actually going to do. Okay, so here, as you've likely heard, so fully homomorphic encryption is a version of encryption. Think of encryption as the starting point that adds some sort of additional homomorphic evaluation property. So for example, here, if I take an encryption of X, there's a way of homomorphically evaluating on the encrypted data to give you an encryption of f of x that can later be decrypted. Okay, so the topic of this talk is homomorphic secret sharing. And in an analogous sort of way, our core starting point, sort of the analog of regular encryption, is what's known as secret sharing. Okay, so as many of you likely know and love, one of the most basic forms of secret sharing is additive secret sharing. So here, think of, I have some secret value, for example, you can think of a group, bit strings or say modular arithmetic, okay? And I take this secret and split it into pieces with a property that each piece on its own hides the original secret, okay? But there's a reconstruction property that if I take these two pieces together, each of which has, in some sense, no information about S, I can reconstruct S again. And indeed, for additive secret sharing, this reconstruction is simply just addition. So for homomorphic secret sharing, this is it starts exactly in the same sort of way. So here I have some secret value, say X. I want to share this, split it into separate pieces, such that each piece on its own hides the input X. We'll want some sort of size requirement here. So for example, that the size of each of these shares shouldn't blow up too much compared to the original size of the input X. Okay, and the homomorphism part here is that if I'm given just one of these shares, I can locally, without talking to the other person, locally do some sort of homomorphic evaluation on my share, so that the output value, so say this is me on the bottom half here, I do this evaluation, I get some value y1, you do the other side, you get y0, and these are now additive shares in the sense that these add up to, so here this is homomorphic evaluation with respect to some program P, and the input X, and the output here is P of X. Okay, so this was like the analog of decrypting and getting f of X before. Okay? So this is really, get yourself comfortable with this. We're going to be talking about this notion a lot. So just to be a little bit more explicit in the comparison here, so compared to fully homomorphic encryption, this homomorphic secret sharing notion is making an extra assumption. So it's assuming that there exist two non-colluding parties. So note if these two pieces of X come together, there's no secrecy at all. You can reconstruct X. Okay, but sometimes, in many cases, this is anyway the case. It depends sort of on your application. Okay. And in fact, so in such cases, I would even argue that perhaps fully homomorphic encryption is an overkill. So this means, for example, here with HSS, you don't have, here with fully homomorphic encryption, you have this public key, the secret key. In particular, this decryption procedure, in some sense, has to be kind of complicated, it has to be complex. Versus here, when you split across these two parties, I can even get the reconstruction so that the analog of decryption is literally just adding two things together. Okay? So, as a function of this, it's an interesting creature, I think. It's neither strictly weaker than, sort of incomparable to fully homomorphic encryption. Weaker in the sense that we make this assumption, but stronger because of this reconstruction. And also, I'm not going to talk about it today, but also if you relax the requirement here and you say that this reconstruction can be more than just an addition, this is also interesting in many cases. But for some applications, you do need this, and I'll focus on this for today. Okay, so because of this splitting across two parties, there's hope that maybe we could have different approaches for constructing this as opposed to fully homomorphic encryption. For example, based on different types of assumptions. I'm cheating here, this is a lattice workshop, but I'm also interested in non-lattice type things, whereas for fully homomorphic encryption, we really don't, in some sense, have a clue how to do that. Okay, in addition, we can hope in various cases that maybe this sort of technique can get better efficiency. Okay, so let's start with a warm-up here. In fact, maybe this has even come to some of your minds, that this... good question. So if you have fully homomorphic encryption where the decryption, you do need an extra property, it's not generic. If the decryption has a sort of nice threshold structure. Actually, I'll talk about that a little bit later. Good question. Okay, so as a starting warm-up, in fact, a very simple construction of homomorphic secret sharing. Here for the class of programs that it can support are simply the linear functions. So x is my secret value, then for some public coefficients a and b, we can try to homomorphically evaluate this. And indeed, if you take a look at this, even the original, the original additive secret sharing scheme, where I just have a random value, and the random value is my value subtracted from my value, this already supports a linear homomorphism. And this is something that was observed back in the 80s and actually sits at the core of a lot of existing techniques for thinking secret computation. Okay, so this, and here, by the way, you don't need any computational assumptions. You can get perfect security with linear homomorphism. So the challenge, and loosely when I refer to homomorphic secret sharing, I'm going to be talking mostly about trying to support homomorphism for richer function classes. And then things become much more challenging and more interesting. Okay, so I'm going to start by telling you a little bit about what we do know about homomorphic secret sharing. And here, as maybe you've seen from the previous slide, the power or the difficulty of achieving HSS scales with the class of programs that you want to support homomorphism for. Okay, so here think about kind of vertically up here all the way up to all possible functions, kind of the analog of fully homomorphic encryption, so fully homomorphic secret sharing. Here's the rough landscape, first of all, beautiful, I'm going to claim. I chose this picture because it has a couple different layers in it. And really, so let me kind of step through some of these different layers. And something that's a bit fascinating to me is that the constructions in each of these different categories, for what we have so far, look totally different from one another. Okay, so down at the bottom, this is what we have already for the class of linear functions. Here, you don't need any computational assumptions. Up at the very, very opposite end, in the high level, we know how to achieve for all possible functions. So all circuits here. This builds on top of a specific fully homomorphic encryption scheme, or rather any fully homomorphic encryption scheme with this sort of threshold encryption structure. So here assumptions is this, say, LWE plus circular security assumption. Okay, bouncing down here now, this class of sprinkling of low-level functions, so simple kinds of functions. A couple examples here are the homomorphism, so for the class of functions, so that I secret shared some input x, and I want homomorphism for the class of equality check functions. So each of these functions is parameterized by some value x prime, and the question, the function should evaluate to 1 if the secret value is x prime, and otherwise should evaluate to 0. So this is an example of a kind of a targeted, very simplistic function class, and there's a couple tweaks on these interval functions and things like that, which are surprisingly useful. And here, these constructions, I'm going to be so bold as to say that these are quite practical. These are fast. People implemented these. They're really only based here on one-way functions, just using pseudo-random generators and using, for example, AES as a pseudo-random generator. This is fast. Something of interest, so here these constructions do make computational assumptions, whereas here we didn't need. And it turns out that you actually have to make this. So there's a lower bounds are known that if you have homomorphic secret sharing for function classes like this, that this implies the existence of one of the functions. Okay, so moving up in the world here, jumping up to the class of polynomial-sized branching programs. So we're going to see a lot of that later today. Just to try to kind of keep in mind what does this mean. For example, this captures log depth circuits, or NC1, also log space computations. Okay, but it's not all circuits can be expressed, as far as we know, as polynomial-sized branching programs. Okay, so here, this is in some sort of mid-level here. If you're not familiar with all of these, don't worry. These are all structured assumptions that each of them individually we happen to know imply public key encryption. Okay, so, for example, DDH is based, so decisional Diffie-Hellman, this is related to partition discrete log. Okay, and LWE, you should know by now. Okay, and the last little piece kind of stuck in here, I would say we really know the least about. So this is, we can capture low-degree polynomials, and what I'm going to refer to as weird PRGs, and I'm not going to explain further for now. But this is based on learning parity with noise assumption. So this is a flavor of LWE, but where the noise distribution is low panning weight instead of low weight instead of low magnitude. Okay, so for today, I'm going to, as we sort of progress across the next 2 hours, these are the two that I'm going to tell you a bit more about. So overall, for the talk, I'm going to start by telling you more high-level things about homomorphic secret sharing, including some sample application regimes. And then we'll start getting a little more into the guts of things with two different types of constructions. So to begin with, there'll be homomorphic secret sharing schemes, constructions from lattices. So I'll touch a little bit about generic, semi-generic, ones from fully homomorphic encryption, and ones for this weaker class of branching programs that avoid some of the FHE machinery. Okay, then in the second part, I'll talk about something that I imagine you've never heard of. So it's something we refer to as pseudorandom correlation generators. And this is an interesting new direction of applications of homomorphic secret sharing. And this is my second cheat. I'm counting LPN as a lattice assumption, so that's not true. Coding, I suppose. Okay, and then I'll conclude and give some comments. Okay, and yeah, so if people have questions along the way, feel free to let me know. Okay, so let's start with the beginning. I want to tell you more about applications of homomorphic secret sharing. Okay, so the first application is the setting of secure computation. So here, suppose I have Alice and Bob, each with secret inputs x and x prime. They want to learn f applied to both of their inputs together, but in such a way that you learn nothing else beyond the function output, f of x, x prime. Yeah, when you first see this, it seems a little bit magical. Is this even possible? And the sequence of really beautiful feasibility results, in fact, getting with our very own Professor Herzliya, show that you can do this for any function. And so either, as we've developed over the years, we know either if you have an honest majority parties, so here you would need more than just 2 parties, if you have a collection, or based on computational assumption. Okay, so the setting where this is going to be interesting for us today is succinct secure computation. So the question in mind is, how much communication, how much do Alice and Bob need to talk to one another back and forth in order to do this evaluation? Okay, so first of all, note that if I didn't care about security, I can always do this no matter what the function of this circuit is. I can always do it with communication bounded by input plus output size. Okay, Alice just sends her input over, Bob does the computation and sends back the output. Okay, so this is sort of what we're taking as a baseline. But interestingly, with security, so we know that we can do this for any function, but sort of all the classical results, for decades in fact, required that the communication now scales with the circuit size. So for example, if you are in some sort of setting where your circuit has very small, sort of tiny little input and output size, and the circuit itself is very big, this is a qualitative gap. And this was a question that was open. We had no idea for decades whether you could push this below. Could you actually communicate something that's subliminal in the circuit size and get secure computation? Then, with breakthroughs of entry and fully homomorphic encryption, this was the first time that we had a solution where you can. And indeed, so here, if you use fully homomorphic encryption, you can essentially mimic this simplistic Alice sensor input over pop sends back, but underneath a layer of encryption that gives you security. So here, the communication complexity for the secure version also scales roughly as input plus output size. Okay, and this was sort of a state of affairs. So I want to show you that this is one of the instances where FHE may, in some sense, be an overkill. So let me show you how, if you have homomorphic secret sharing for some class of functions, this implies two-party, here this 2PC, I'm using to represent two-party secure computation for a comparable class of functions with low communication. Okay, so here I've brought us again back to this homomorphic secret sharing. So suppose that we have this as a tool. Now, how do we use this for Alice and Bob? Okay, well, one way you can do this is to have Alice and Bob run an off-the-shelf generic secure computation protocol, for example, the Yaus-Garland circuits or GW and so forth. Okay, so here they are doing sort of a circuit size cost communication here, but the circuit that they're computing is not the overall circuit C, okay, which is we're saying that's the big one. The circuit that they're evaluating is just the functionality that takes their inputs that are stuck together and generates homomorphic secret shares of the inputs. Okay, so this is something that can scale roughly with the input size, but not with the size of the function itself. Okay, so once they do this, now this is the communication. The output that they get, each one sort of just spits out their share. They don't learn anything else. This is the guarantee of this secure computation protocol. And now, the homomorphic secret sharing has essentially allowed us to push out the computation of the circuit, this heavier part, to locally homomorphic evaluation. Okay, so once we get these shares, without talking to each other, we homomorphically evaluate, and then we can simply exchange the shares to learn the final output. And actually, it turns out, so if this reconstruction is exactly addition, then this is even secure as it is. We can just send the shares to each other. More generally, if you could have just, for example, done some sort of secure computation here. So this is one of these instances where having compact shares, but not necessarily additive reconstruction, would still suffice. Okay, so taking stock here, what is the communication that this protocol has? So it was the communication of this, which is roughly, so here now, this lambda is going to represent a security parameter, sort of the key sizes of these things. So the communication here is something like the size of the inputs times, say, some polynomial security parameter. This is coming from the cost of whatever the circuit size is for the share, this HSS share function, and the overhead of doing the secure computation with that. Okay, so it's this, which is roughly sort of input size, plus these shares, the additive shares that were exchanged, are exactly the size of the output. Okay, so this is getting us back exactly to roughly input plus output size as we wanted. Okay, so this is a general framework, and now plugging in from the constructions of HSS that we know, what does this give? So again, we knew from fully homomorphic encryption, we could get succinct two-party secure computation for circuits. So this was a general result, but of course there are some downsides with FHE in of itself. Okay, so for example, the fact that we really only know how to get this from some window of assumptions based on noisy encoding lattices, or relatively high concrete costs altogether. Okay, so plugging in for HSS, I've grayed this one out because it's not so interesting. If you look at the very high construction that we have on this landscape, HSS for circuits, we know how to get it, but it anyway builds on fully homomorphic encryption. So that's not anything new. But now if you take a step down to this middle complexity, medium region, this class of branching programs, if you plug in our constructions at that level, this now for the first time actually gave us succinct secure two-party computation protocols from assumptions based on mathematical structures that were not lattices. Okay, and indeed, actually, as we'll talk a little bit about today, even if you are using lattices, there's potential for efficiency gains. Okay, so this is one application, this low communication secure computation. Another application setting I want to talk about is what's known as private information retrieval, and in particular, the two-server case of this problem. Okay, so here we have two non-communicating servers, which each have some public database. Okay, so keep in mind, we're not trying to hide anything about the database. What we are trying to hide is that some client comes along, wants to access some item I, maybe some embarrassing information or something, and he wants to access this item, but without revealing to the servers what was the index I that he was interested in. Okay? So a private information retrieval protocol is some way that they can communicate back and forth, such that the following properties are satisfied. Okay, we of course want correctness, that at the end of the day, the client actually does receive the ith entry to the database. The privacy requirement, it's roughly, so there's going to be a mask popping up here. What this is going to formalize is that each one of the servers on their own, if they're not talking to each other, does not learn what I was. What here I is the index. Okay, so formally for any possible pair of indices, if I was looking for I or I prime, and for each one of the servers, if you look at the distribution of the view of the server, so including the messages going back and forth, whatever randomness it had locally, this is a distribution, looks very similar in the two different cases. You can't distinguish whether you were asking for item I or item I prime. Okay, and finally, so you can always, there's always a solution to this problem where the database or the server just sends the entire database to the client. This gives you perfect privacy in the sense that there's no information about the index leaked. But obviously this is not a very satisfying solution. And so to actually call yourself a private information retrieval scheme, you need to have a non-triviality condition that the communication is strictly less than the database size. Okay, so I'm going to, in a two-step process, I want to tell you how homomorphic secret sharing can give you solutions for this problem for, in fact, more generalized types of queries. So for example, something like that the client doesn't just want to look at a particular index I, but possibly something more general. For example, say he wants to know how many items in the database satisfy the secret predicate P, and P is what he's trying to hide. Okay, so for those of you, if anybody's seen this, I'm going to start with something that's roughly the equivalent of how you would use fully homomorphic encryption in a single server case. So here, I have, as the client, I got this secret value P. I can homomorphically secret share this into these two parts, so we're trying to keep my arrows sort of consistent here, and give each piece to one of the servers. Okay, and note, by the way, so the secrecy property of the homomorphic secret sharing automatically now gives us the privacy guarantee that we need. That whatever this share is not leaking any information about what my private predicate was. Okay, so now, and again, this is just a generic solution. I'll be more specific on the next slide. Okay, but you can think about this database defines some function. Okay, so think of this as a function db of some predicate. So the predicate is the input to this. Where this function is defined exactly as outputting for this database how many database items are satisfying this predicate. Okay, so this is kind of a generic sort of approach. But certainly, if your homomorphic secret sharing scheme supports this type of functions, then really what the servers are doing is they just want to homomorphically evaluate their shares with respect to this function. This will give them each some share. This is the output share. And the correctness guarantee of HSS, this sum of these shares is exactly the function db applied to the secret predicate b. Okay, so this also gives us correctness, and it does give us non-triviality as long as whatever these outputs are and everything are smaller than the database size, which is pretty like this. Okay. However, this is a feasibility statement, but it's pretty heavy in the sense that defining this, we're thinking the database is some huge thing, and we're trying to homomorphically evaluate this huge function now on some predicate. And here's one instance where the specific additive reconstruction property of the HSS can actually really come to save the day in some sense. Okay, so the goal now, I want to describe to you something that's a little more fine-grained of how to achieve the same task, which will give you better complexity. And the idea is that I can split my sort of complex function, which we called db from the previous slide, into a bunch of simpler functions, dbi, let's say, such that the output of what we really want is equal to the sum of the outputs of each of these things. Okay? So for example, let's go back over here. Think of, for suppose that what we wanted to know was how many of the database items satisfy this predicate. So we can define now for each database item on its own a simpler function which just outputs 0 or 1. Does this database item satisfy the predicate or not? Okay, and again, so we're not actually going to learn these values, but for now, you'll again send homomorphic shares of the predicate p. And now we're going to homomorphically do n separate evaluations, one for each of the database items. Okay. So what does this give us? This gives each of the servers now has n separate outputs. Okay, and suppose that they sent over all of these outputs. Okay, this is very long. We'll get rid of this soon. But if we were to send over all of these outputs, then by the definition of this function, really what the client wants, so here, what is this? If I take for any one of these, say the first here and the first here, and I add them up, this gives me exactly this database sub1 function applied to the predicate. So this would give me exactly either 0 or 1, depending on whether the first item in the database is satisfied. Okay, so this, now if I take each of those, this is sum it over all of the different database items, this is giving me exactly the count of how many database items satisfy the predicate. Okay, so first one. Alright, well, one fantastic thing about addition is that it is, in fact, commutative. Okay, so another way I can sort of think of this as a 2n different terms I'm summing together. In this case, I'm first summing them across in pairs and then to the n. But I could instead split it into two separate sums across the database. Okay, what does this buy us? Well, so that first of all, this is the same output, this will give me the same thing. But each of these is the size of one output, and it's something that each of the servers respectively can compute on their own. So effectively what's happening, we did each of these evaluations, this gave us each of these output shares, and the point is I don't need to send you each over individually because you're just going to add them all up anyway. So instead I can collapse this down to the size of one output instead of n, and send this sum back, which is enough for you to reconstruct. Okay, so this is a general framework that now if you're looking at specific predicates on a per item basis, this is enough. This is all that you have to be able to support in terms of the power of the homomorphic secret sharing scheme. Okay, just good. So at a high level, this gives you some nice properties. So the small communication in both directions, going from client to server, this is comparable to the size of the HSS shares of my predicate. And the interesting thing, actually, one of the interesting things, is the message coming back is exactly the size of the output. Okay, so for example, suppose that whatever I wanted to learn was actually a single bit. Each of these sums is exactly a single bit. So this is kind of the optimal communication on the way back that you hope for. Okay, and for simple but interesting types of queries, this construction can be quite efficient. So as one example, if we go back to the standard notion of private information retrieval, where I'm just trying to access a particular item index I, the solution currently stands as the best, the cheapest solution in this entire computational privacy regime. So just really quickly, this is not really the focus of the talk, but to explain this slide. So the statistical versus computational privacy, this is going back to when the server's view for index I versus index I prime, that they're indistinguishable, whether this is in a statistical sense or computational. Basically, whether you're making computational assumptions. So over on the statistical privacy side, this is, for the one server case, we know it's impossible. For more servers, there's a lot of actually really interesting developments with local immutable codes and other areas, not so much tied with cryptography. But these are a fairly n to the little o of 1 cost, and they're quite complicated. Versus over here, if you're okay with two servers, so I should mention actually one server private information retrieval. So this is the comparable version, but where there's only one server, not two that aren't talking to each other. This is something that you can get with fully homomorphic encryption, and you cannot get from homomorphic secret sharing. So I'm playing a fair game here. But if you are okay with two servers, if you're in a setting where this is a reasonable assumption, then the costs drop quite a bit. So for example, these use lots of public key operations, even ones not using homomorphic encryption, versus using our techniques from the previous slide. We can plug in even just a second, homomorphic secret sharing schemes based on one-way functions, and this is quite fast. Question? Yeah, so I'm not sure you heard all your question, but let me answer what I think may have been your question. Indeed, here, so there's a lower bound showing that if you have such a thing, you actually have oblivious transfer. So you can't hope to get it statistical with a single server. Is that what you're asking? If not,
anyway, if you assume some dislocate or assumption or factor assumption, under this assumption...
no, good. Then that pushes you already over to the computational inherently. All right. So, good. So this closes up what I wanted to say about private information retrieval. Let me close up this application section of the talk, just by giving you a little bit of a flavor here and there of some other things that are going on with applications of homomorphic secret sharing. So for example, this is something that was picked up outside of our line of research, and very interesting, using exactly these one-way function-based techniques for homomorphic secret sharing to get efficient, these are actually concretely efficient secure computation protocols for random programs. Here, just to give one sentence about it, you're essentially actually using the private information retrieval, the two-server setting in here. Again, let me actually maybe go a little bit quicker. So here we have techniques for for proving statements that are split across the verifiers. So for example, suppose I want to prove to somebody that some statement is true, but now you're actually two different people, and neither of you knows the statement. But somehow, between the two of you, maybe you have pieces of the statement, or you have additive secret shares of the statement, and I want to be able to convince you as two different verifiers that the statement is true. And this has a lot of really interesting applications, again, for secure computation. This allows us to get some pretty cheap compilers of trying to go from, for those who've heard of this, go from semi-honest or passive security to active security. Also, kind of in a different setting, secure computation, mixing Boolean and arithmetic operations, and also some applications in areas I wasn't really expecting. It's been kind of a fun roller coaster ride working in this area. So for example, implications to complexity theory in terms of worst case to average case reductions, or in algorithms. It turns out that one piece of the construction based on the DDH problem actually has applications or ties to locality preserving hash functions. So here's there's no security involved. These hash functions are just, you want to be able to hash two things that are close together to something that's close together. Okay, and much more, and I expect there to be much more in the future as well. Okay, so yeah, I'm going to figure out exactly about time here. So let me start with part one. Now we're ready for part one. I want to say some things about homomorphic secret sharing constructions from lattices. Okay, so the first thing to mention is, it came up in a question, is that if you have a fully homomorphic encryption scheme where the decryption procedure has a particular useful structure. So let me describe this a little bit. But if you have such a thing, then this gives you homomorphic secret sharing already for two parties. Okay? So what is the construction going to be? Well, suppose that I give you have this fully homomorphic encryption. So the secret, the HSS shares, okay? What you're going to do, so this is, you start with your input, you generate a key pair through homomorphic encryption. And the two shares are going to be an encryption of W, here this box represents encryption. And, oh no, this is very important, this should be an SK1 pair, okay? There should be additive secret shares of the secret key. Okay? So as you might expect, homomorphic evaluation is going to correspond to homomorphic evaluation with the FHE. Here this is on the encryption of W evaluated. Okay, but this is not the end yet. This is still not achieving what we want. Why? Because now, that's great, these give us encryptions of what we want, but somehow now I want additive secret shares of the output Y instead. So the second phase is going to actually take this encryption of the output, this is, so Y is C of W here, and use the piece of your secret key to decrypt that. Okay, so what do I mean by threshold FHE? I mean there's a collection of FHE schemes that have this property that if you, there is some procedure for doing a threshold decryption with pieces of the secret key, such that when you add these things together, this gives you, I decrypt the encryption with my piece of the key, decrypt with your piece of the key, and now these add together to get the output. Okay? So does this make sense, this framework? Again, kind of the point is now the homomorphic evaluation is these two different parts, okay? So in the first part, this is where we're doing for example, ciphertext multiplications, all these standard actions of the fully homomorphic encryption, and then at the end, there's one decryption. Okay. So I say it again, but there's no security for what? Good. Did we achieve? So here you do, because I'm not giving you the key, I'm only giving you pieces of the key, additive secret shares of the key. So first of all, to answer your question about the security definition, you can exactly think of it as a semantic security game. So here, say this is the adversary, it's one of the two people. And by the way, everything in this talk I'm talking about semi-honest or passive adversaries, I'm not talking about active. Okay? So this, the security game is semantic security in the sense of saying, even if I choose a W and a W prime, now you give me a share of one of those two, I can't distinguish which one I came from. Okay, and here, yes, so it's important that this is not the full secret key, that this is an additive share of the secret key, so that doesn't give you any. Wait, what? Yes, exactly. Here, this is an encryption of W, and this is an additive share of the secret key. Okay. Okay, so here I want to give you a slightly different angle view of existing results in HSS. So this is the, here now, computational overhead mapped with respect to expressiveness. So in this corner, this is where we have these simple functions, things like equality match and so forth from one-way functions. And on the other end, this is what I just described in terms of using threshold FHE. Okay, although, so there's some downsides to this. For example, you do have these noise growth and ciphertext multiplications. Okay, backing off to these branching programs, so the DDH-based construction exists, but I'm putting it kind of high in terms of computational overhead. And this construction, so this is one of my babies or whatever, I'm very excited about it, but admittedly there are plenty of downsides. So for example, in this construction from DDH, you can't get rid of error. The construction has 1 over polynomial error, and it also has limitations, for example, of the size of the plain text that you can store. Okay, so I'm sort of easing now into a recent work where we were asking the question to ourselves, okay, so we know that if you have FHE of a particular form, this gives you HSS, but really one of the goals was to try to see if you could bypass FHE. So is it possible to build HSS from lattices without FHE? Okay, and so I'm going to go with yes, but maybe before I answer that question, I should say a little bit about what we even mean without FHE. Okay, so this is not an official statement, and there's not some sort of separation or anything of that form. But what I mean here is there some way to mimic? So again, if I'm giving you lattice-based assumptions, but not FHE, and I want to get HSS, but without needing to be able to use these ciphertext multiplications. Okay? So here, indeed, this is what our goal was and what we were able to do. Roughly so now what we can do in this construction is to replace these ciphertext multiplications and roughly replace them with some form of decryption. Okay, so it's going to be this cross. Good. So let me try to see how far I can get before the break. I do want to tell you a bit about this construction. Okay, and before I jump into the construction, let me tell you a little bit, just of a pause of why should we care about branching programs? I keep talking about these branching programs. And as I said before, this does capture log depth, log space computations. But to just give you a little bit to keep in mind, here's some examples, things like min to distance, length and vectors, a lot of different statistical calculations, and so forth. But this is actually a reasonably motivated class to try to study. Again, I'm not going to define the standard notion of the branching program as we normally see. What I am going to, how I'm going to represent these programs is going to be useful to think about what we refer to as restricted multiplication straight line programs. And basically all you need to think about is the following. Okay, so I'm thinking about programs that are represented with 2 types of data. There's the input, okay, and then memory values as we're performing various computations. Okay, we're going to be able to support the following 4 operations. Okay, so for example, I can take an input, I can load it to memory. If I've got 2 different memory values, I can add them together. Something that's in the memory I can output. And the interesting one is that I can support homomorphic evaluation of a multiplication, but only if that's one of the 2 things being multiplied was an original input value. Okay, so as a sanity check, the thing that's missing, why is this not all possible circuits? Because I know addition and multiplication are complete for gates. And it's exactly the thing that's missing is multiplying two partial computation memory values with each other. Okay, so if you're viewing this as a circuit, think of it as every multiplication gate, one of the wires needs to go all the way back up to the input. Okay, I'm actually going to skip this slide, partly because you've been seeing it a few times today, I would say, and also partly because I'm not actually going to use it. So in this construction, we're using sort of as a black box properties of encryption schemes that are known to be based on learning with errors and the learning with errors version. Okay, so we won't actually look at the structure of it itself. Okay, and a little bit more information about this. So the bottom line of this construction is that it's got these appropriate benefits here as compared to the constructions from either homomorphic encryption or DDH. Okay, it requires various tricks for using lattices in a distributed setting. I'm not going to have time to talk about some of the other interesting optimizations. For example, if you're looking at degree 2 programs or trying to do batching of parallel SIMD operations and so forth. Okay, but I do want to give you a flavor of what does the construction look like. And to do that, let me start by giving you a little bit of information about the structure of the construction based on DDH, because we're going to have a similar sort of framework in a sense. Okay, so remember, these are the input and memory values we want to somehow mimic. Okay, and there was a reason why I had these goofy colors on the other slide. So for while we're doing these computations, we're going to sort of store values. Remember, I'm trying to describe how the two of us do these homomorphic evaluations. Okay, so we're going to store values between us in two different ways. One, which is represented by these green boxes here, will be encryptions. Okay, so I have an X in a box. This means an encryption of X. And the memory values are going to be some flavor of additive secret shares. So here, this is why there's these two things here. If I say X in yellow versus X in orange, these correspond to the two different additive secret shares of X. Okay, now for each type of computation, let's take a look at how we could try to support homomorphic evaluation. So for example, say I have an addition here. Well, this is good news, because if we're storing memory values as additive secret shares, this is already additively homomorphic. Okay, so there's directly a way of taking these shares of X, shares of Y, and getting shares of X plus Y. Okay, and S is typical. The tricky part here is multiplication. And this is where we're going to have this limitation that one of the values being multiplied has to be an input. Okay, so if I have an input value, this means that I have an encryption of X. And in fact, both of us have an identical copy of an encryption of X. Okay? And so now what we're going to describe is a way of taking an encryption of X and say additive shares of Y. It's actually going to be a little bit more information. And trying to get, so remember, I want to take an input times a memory value and get a memory value out. So I want these additive shares of X times Y. Okay, and this multiplication really is the tricky bit. This is the expensive part. This is the one that, for the DDH construction, it's actually inherently requires one over polynomial, not negligible error, and restricts the plain text size in the previous construction. Okay, so our construction now is going to take a similar flavor. So we're also going to be storing information in these two ways. Okay, but the encryption scheme that we're going to use is going to be one that has a property of nearly linear decryption. Okay, so what does this mean? I'm going to be a bit more specific here. So let's think about two different modulus spaces. Okay, I've got ZQ, which is a bigger one. This is where the ciphertext elements live. And ZP, which is the smaller size, which is the plain text space. Okay, and if you sort of flip through the literature, you'll see that the structure of many either LWE or ring LWE-based encryption schemes satisfy the following property. Okay? That there exists some linear function, I'm going to call it lin dep, Okay, here linear in the secret key, such that if I do this linear function, okay, this is not full-blown decryption, but if I apply this linear function to the ciphertext and the secret key, or linear in the secret key, then what I get is almost equal to, so it's this value plus some error mod q. Okay, here this is q over p times x. So for example, suppose that p was 2, this is maybe looking a little more familiar for you. See that when you do this decryption, you get some value that's either close to 0 or close to q over 2. Okay, so we'll start with such an encryption scheme, and let's try to figure out if we can do first attempt at getting multiplication. Okay, so remember that this function is linear in sk, and the idea is to emulate multiplication by decrypting with pieces of the secret key, but not, so pieces of the secret key times something. Let me explain. Okay, so because this is linear in the secret key, that means if I have additive shares of the secret key, then I can split, so here, if I add them together first, this is the normal decryption with the secret key combined, but because this is linear, I can split this into the sum of these two different parts. Okay? So this is something that each party can do on their own. And now if we were to do that, then add them together from the nearly linear decryption property, it means that I'm approximately equal to here. Okay, so now brace yourself for this amazing animation here. So here, in one moment, I have shares of the secret key. In the next moment, I have shares of y times the secret key, where y is some other value. Okay, so suppose that we did have that. So now we have these additive shares of y times the secret key. So what does that give you? Well, again, this function is linear in this position, and this y is just some constant value. So this pops out the front. I get what I had before, and now this is what I had before times y. Okay? So this is almost what we want. What is this saying? This is saying, essentially, if I do this, and you do this, then what we're getting is almost additive shares of something related to x times y. Okay, so the first problem is this squiggly equals. Okay, this is not equal to. In fact, it cannot be equal. The decryption can't actually be linear in the secret key. So how can we somehow try to remove this error noise? Okay, and this is the first step here of a local rounding procedure. Okay, and essentially, so this there's a procedure round. What is it? Explicitly, it takes, so round of z will take this share, whatever you have, multiply it by the reciprocal, by p over q. This might, because p is less than q, this is some fractional value, this might not be an integer. It takes that value and it rounds it to the nearest integer. Okay, but if you go through and do the math, then in this case, if I do the rounding locally, you do your rounding locally, this is almost free, so in many times, this is the same thing as if we first added and then did the rounding. Where the probability of this not taking place corresponds roughly, so there's some small zones of bad shares, if we happen to have bad shares, where we're sort of straggling one of these edge points. And the probability of these bad events occurs with probability roughly, so here it depends on the size of the payload. This is talking about how far the shares are apart to begin with, times this value q over q. Okay, so if you are in a setting where q is, much bigger than p, then this error can be small, can be negligible. Okay, as a caveat, this does require now, and in fact our final solution has a superpolynomial size modulus. This is something to try to remove. Okay, so what do we have so far? So suppose that we have these shares, these additive shares of y times the secret key, and we had an encryption of the value x. This was the linear function. So if you do spit this out, then do the rounding, this gave us, with high probability, now additive shares of x times y. And this is what we wanted. Okay? But now there's another sort of sticky point. So here, in order to do, really what we were trying to do is to get from here to something that looks very similar again, so we could keep doing another multiplication. Okay? So the first issue is that in order to do another multiplication, this shouldn't be x times y, it should be x times y times the secret key. Otherwise, how am I supposed to do this linear decryption step over here? I don't have any information about the secret key. Okay, and this can be solved by, instead of just giving an encryption of x, of actually giving an encryption of x times the secret key. So if you had such a thing, then what does this end up doing? Now this multiplication of the secret key is going to pop into here, and this is exactly what we're going to get as the shares here. Okay, so this is, you know, making progress. And there's one last potential issue, okay, which is that, so these, when you actually go through and you look at this rounding procedure, we started with additive shares modulo q, this big modulus, where the ciphertexts are within. But when you do the rounding, you're doing this, you're sort of dropping down to a different modulus level. And the shares that we get are no longer mod q, but they're mod p. Okay, so for example, to kind of just take the straightforward approach, if you had to drop down the modulus each time you were doing a multiplication, this would be way too expensive. Okay? So the second observation is that actually, essentially the same argument from the rounding saves the day, and we don't have a problem. Okay. So note that this modulus lifting, where I want to somehow go from Q down to P and back up again to Q again, ideally if we could. It's not clear in general that you could do this. So for example, if I have additive shares mod 3, say 2 plus 2, oops, 2 plus 2 is 4 mod, okay, so yeah, these are not equal to each other, don't go with that. So in general, you can't just sort of change the modulus and hope that your shares are still going to be valid shares. But it turns out that if so if the space where your shares are coming from are much bigger than the value itself, then actually the probability, if you have these are randomized secret shares, the probability of being in this bad case where we sort of crossed over the threshold, okay? So if I'm looking at the entire space of possible shares here, there we are, but really, so the shares for one of them live here, and unless I'm really unlucky and happen to get that one of the shares is right near the border of the smaller modulus, then the shares mod p are actually already shares mod q. In fact, they're shares modulo over the integers. Okay, so yeah, this was maybe a little bit fast and sort of tight on time. So let me just sum up, and I'll be happy to take questions during the break if you're interested. Okay, so to recap, what was the construction? So to give homomorphic secret shares of some value x, I have two parts. So essentially you're going to generate a public key secret key pair for the encryption scheme, okay? The shares will give you, each person will get some additive share of the secret key. This is enough for you to kind of get moving. And encryptions of my input, the x I'm trying to share, times the secret key. Okay, and the main idea is if you didn't follow the specifics, that's perfectly fine. The takeaway is that you can now effectively do a multiplication via the operations of decryption. Where instead of decrypting, so I'm decrypting with these shares of the key, and what you'll end up getting once you do partial computation is you'll have shares of the key times some value. And when you're doing this decryption with that, it sort of pops in that value as a product. Okay? And now here, this allows you to keep going and going. Okay, and a couple comments here. So this allows you to, all these rounding and lifting and so forth, requires that the magnitude of the values are small compared to these P and Q. Okay, so this does mean that the costs here grow with the size of the magnitude of the values that you're computing on. Okay, but this does give you, for any branching program with some bounded magnitude, as long as the biggest magnitude you get is smaller than P, which is smaller than Q, in fact, scalable, so by this magnitude. Okay, and so I didn't hear any yelps yet, but this is always a little bit suspicious, right? So I'm telling you, you should encrypt your secret key and hand it out to the world. And this is always something you should be wary of, because this requires circular security. Okay, and by the way, this is something that always comes up with non-level fully homomorphic encryption, that you have to give out this information, which includes the encryptions of pieces of the secret key. But something that's really interesting, so for FHE, to date, kind of our only real solution is to kind of boost the assumption, to say, well, assume that this key is still secure when you give this out. But in our setting, this actually already is implied. So just the property of this nearly linear decryption already implies that it is safe, that it is circular secure for this type of function. Okay? And even something a little bit better, if you look into how this is proved in these works, how this is done is basically by showing that if you just give me the public key, I can anyway generate something that looks exactly like an encryption of this secret key. And this is something that's not only a proof technique, but we can actually use it. So for example, if I want to, how can I generate something like this in a public key setup sort of way? So for example, suppose that I want to do homomorphic secret sharing with two people's inputs. And kind of combine them together, so neither of them can know the secret key as a whole. But this gives us a procedure of just taking the secret key and their input and generating these encryptions to put into the system. Okay, because I'm out of time, I'm not going to talk about this, but just to recap, that you can get now to server here for these branching program queries and some plug-in numbers. Okay, so I'll leave the summary up and call it the end of the first hour. So go break.